Greetings to all of you. My name is Shashwat Bhattacharya from National Tsinghua University in Taiwan. Thanks to the IEEE Council and the organizers for giving me the opportunity to present my work. Let me share my screen with you. The, top, the topic of my presentation is a novel thermal piezoresistive coupled resonator for implementing mode localization for mass sensing. This work demonstrates for the first time exploration of the phenomena of mode localization in TPR transduction, attaining a decent quality factor of 1367 in ambient condition. Let me briefly go through the content of the PPT. The presentation starts with the introduction that consists of the motivation behind the work along with the prior state of the art. Also, in this, the choice of the TPR and the mode localization is explained. Next, I would introduce the fabrication flow of the TPR followed by the measurement of the coupled TPR. Then I'll conclude with the presentation. Let's start with the motivation. The motivation behind the work involves the application that can be targeted with the design of such coupled resonators in ambient condition. The help received using the of phenomena of mode localization and the advantage of the transduction. The resonator performance is critical for it to be used as different applications such as air pollution monitoring systems, portable biosensors, and oscillator filters for IoT applications. This slide shows some of the prior state-of-the-art comprising of demonstration of MEMS oscillators, biosensors, as well as mode localized particulate sensors, and also the different in-plane TPR. This mode localized sensors shows the highest reported quality factor of 600 in ambient condition. We also show the single degree of freedom DR-TPR that has been enhanced to suit this work. Let me briefly mention the phenomena of mode localization. The explanation involves three major points: breaking the symmetry, modes selection for sensing, and sensitivity calculation. Take an example of piezoelectric out of phase Lamy resonator. If for a symmetrical or balanced weakly coupled resonator system, a small perturbation is made, it introduces in one of the resonators, the propagation of the vibration gets spatially confined. This confinement reflects strongly in the magnitude of the resonator response as can be observed in the figure. Depending on the input and the output, we would notice for a specific configuration, when multiple modes are excited, we would choose a particular mode for sensing. The choice of the mode is made considering the mode that has the highest amplitude when measuring the frequency response. For example, in the figure, for the three-ordered system, we have three peaks corresponding to different modes. We choose the third mode as the energy confinement is more dominant here in the third mode and neglect the others. After the choice of the mode is made as a third mode, next is finding the sensitivities. S delta F is sensitivity for the change of frequency with the change in mass perturbation for the third mode of resonator 1. S delta A is the change in sensitivity for amplitude change A1, where A1 corresponds to the amplitude of the third mode of resonator 1, and SAR, the sensitivity of amplitude ratio A1 is to A3. The use of mode localization leads to an increase in the sensitivity of the resonator compared to their single degree of freedom counterpart. The amplitude ratios are insensitive to common mode changes like ambient temperature and pressure variation. Two of the major improvements that can be explored in this area are having high Q in ambient conditions and self-oscillation of the sensor. Following are some of the features of the thermal piezoresistive range of the thermal piezoresistive used in this work. It has simple fabrication, large actuation force, high power handling, and low driving power as compared to the other capacitive counterparts, IC compatibility, and self-sustained. We have to accept some of the disadvantages of the system as well. While the TPR is concerned, it consists of three of involvement of three of the subsystems that includes the electrical, thermal, and as well as the mechanical domain. It consists of actuation with the help of AC and DC at the input, and we use we sense the output motional current using the DC at the outputs as well. Next is the design and simulation of the coupled TPR. The 3 degree of freedom DR-TPR consists of 3 ring resonators marked as R1, R2, and R3 in the figure. It also consists of 6 transducer arms used for differential drive and sense configuration. The design of the 3 degree of freedom involves 4 design considerations. Firstly, choosing the in-plane rotation mode as shown is the figure on the right that would reduce the viscous damping in ambient condition to attain the improved value of Q. Secondly, the consideration of choosing the differential port to improve the signal to feedthrough ratio has to be made. Thirdly, the design consideration must be made to couple the resonator with a notch, with the notch to select the point for low velocity coupling. Fourth, the the coupler designed to have a trade-off between sensitivity bandwidth, nonlinearity, and dynamic range. This shows the simulated frequency response of the R1 and R3, and the first dominant peak corresponds to the first mode, and third one to the for the third mode. The second 3 degree of freedom is neglected. The second peak of the 3 degree of freedom is neglected due to the above mentioned reason. The mass is perturbed at R3, and the frequency is measured at R1 and R3, and showing the phenomena of mode localization. These are the simulated normalized sensitivity response of the system, and we can see the amplitude change. The sensitivity has been recorded as around 0.02, and for amplitude change, the sensitivity is 26, and for amplitude ratio, it's around 65. Let's go to the fabrication. As far as the fabrication is concerned, we used 40 micrometer SOI that has been n-doped silicon with 100 orientation and resistivity less than 0.005 ohm centimeter. We use 150 nanometer of TIN as the metallization, and we use 1.7 PECVD oxide as a mask for deep silicon etching. We use HF release at the last, and this is the SEM image of the fabrication device. Let me go through the measurement. This shows the inject printer along with the DOT from Advanced Nano Products, and we put multiple silver droplets on the DOT on the resonator 3. The measurement, this shows the measurement response. The measurement of the 3 degree of freedom DR-TPR was done using vector network analyzer. The middle of the resonator was chosen for driving with a DC bias of 35 milliamp and 10 dBm AC power. The resonator R1 and R2 were chosen to sense the signal. The choice of the resonator of driving and sensing is important to attain the quality of the transmission floor as low as minus 75 dB. The quality factor value of the third mode is 1367 with the stop band rejection of about 10 dB. The graph shows the frequency response of the 3 degree of freedom DR-TPR transmission measured at R1 and R3 before and after the addition of mass on R3. We particularly focus on the third mode, and we can see the amplitude changing at from 381 to 471, 477, and as well in the last graph, and for the third one, it changes from 658 to 608, and hence we can see how the confinement is happening, and we find out the experimental sensitivities of two using two data points before and after putting the mass of 2 nanograms, and we get the sensitivity values of 0.0445, and for delta A we get around 92, and for the amplitude ratio we get around 131, which shows the increased sensitivity. Let me conclude with the presentation. The three degree of freedom DR-TPR for eigenvalue variation and energy confinement has been successfully demonstrated in ambient condition for the first time using using TPR, and with such an high quality factor in the range reasonably for that will open the door for different realizing different mass sensors. The inherent improvement in sensitivity is due to the mode localization, and we can explore more modes in future for in plane, and the integrated MEMS can also be made. Let me stop to share the screen, and thank you, and I'll be very happy to address any questions from the listeners.